Okay, so hi Carlos. I restarted this because I suck and don't look at me. This is my second angle. You can see my screen or whatever. Um, we're live from Calvin's room. He set up a table for me. Thanks, Calvin. Shout out to Calvin.
You're welcome.
Shut up, I didn't tell you to talk. I'm just kidding. I messed up just importing everything, so we're gonna import dumpy. What? It tells me? Interesting. Um, does it tell me? Okay, dot but plots. Ooh, what? Um, I didn't know you could do that. It knows. Okay. We have to do the Jackson Numpy as you know? No, you don't know. No, it doesn't know. We have to do a Jax dot configure. We have to update this. It's going to be a Jax. We have to enable this x64 file thing, and it has to be true. We love Boolean, right? Right, guys? By one and only viewer. Oh man, funk tools. Okay, it knows. Okay, import. Hey, there we go. Finally, let's run this. I can't say bad words. What does it want? Import Jax Numpy as JNP. Maybe it's Jax.numpy. Hey, there we go. Let's go, Carlos. We can start on the next part. Let's call it part one. I'm making Calvin laugh over here. Too bad Hawaii doesn't laugh at your jokes. I'm just kidding. Okay, using closure. I'm only using humor because I'm very upset with this homework right now. Okay, let's go. Okay, let's go. Let me compose myself. Okay, Carlos. So I know this is supposed to be a professional video, apparently, according to Calvin, because you reminded me that these are going in our portfolio to show to our employers. Well, I don't think I want to show them. So, using closure, right? Which is a programming, a coding thing where you have a function and you refer to it in another function and it remembers where it is, like a missile. You know, the missile knows where it is at all times. The missile knows where it is not. Explain and code higher order function returns functions. Very nice, Sarah. So, what we want to do first is actually create a 2D vector. I'm gonna call it V as a numpy array. So np array 0, 1 to 0. So np. It doesn't like me. Let's see. Ooh. Realize I messed up. Yeah. And yes. And if I want to do a 2D vector, then there has to be 2, 1. She's good. Okay. Next. Okay, so what we're gonna do next, actually, you might as well just start a going to rotate the 2D vector matrix. I felt okay. So we're going to define define a variable which we have to compute a 2D rotational matrix from our thing. So we're going to use theta because we're using circles later on, so theta makes sense. Define def rot matrix. Ooh, she's pretty. Why is it? I'm gonna have to do sine and the cosine of our theta. So sine. Yeah, we're gonna use Jimpy sine. Yeah. Wait, no. Oh, wait, that's not what we want. Sine of our theta. Where are you done? Cosine is equal to p dot cosine of our theta. It worked. Okay. But return the array. So if I do this right. X sine. And wait, what to do? Sine. Let's use that. And we're off to the races, folks. Okay, what we want to do now is define or create an array from 0 to 2 pi of angles, or array of angles 0 to 2 pi, and using linspace. So, and we're gonna collect thetas. I think I have to. You know what? Never mind. Ah. Linspace 0, 2 times. Oh, thanks. Well, at least you can't see that my meeting will end in 10 minutes. It told me on my screen. Okay. How do I get pi? Or do I use NP? Pi. Can you be pi for me? Yes. How many points do we want? We want like you use 120. I'll use 120. And let's see. Endpoint is equal to false, I guess. Let's see if she does. That is the same warning that you got, I believe, during class. Falling back to CPU. Cool. Next. Okay, so what we want to do is we want to make an empty list of our X and our Y values, and then every point S, and then for all our for loop for all the theta in thetas. And I think I just had a brain fart. It's okay. Empty list for all the theta. Thetas. At least, okay, yeah, I know it's not complete, but bam. It still works though. Right? And so then, since I tested that, I want to have or rotate my vector v by theta and then put it into v rotational, I guess, v rot. So let's see, what's the rotational matter? Good, good. V. Oh no. I think that works. And then I have to append the V rot. Miss MATLAB. Oh. What? It's true. Zoom. Oh wait, not Zoom. Why am I talking about Zoom? Zoom has a $sign on there and it makes me upset at the V because that's what we're using. But we have to append, so save what works. I don't know. Tuples. Oh yeah, I forgot about those. That word. That's not how you pronounce it, is it? I'm gonna have to clip that, maybe. In series. Do I need to MP it on? No, I think that's how it is done. Okay, now I know why there was like an extra line of coding that I didn't even put in there. But I didn't put the NP whatever in there earlier, I think. I assume. I got rid of it also during the pause. But we need to stop doing that. that really already 27 lines of coding? Favorite part, making a subplot. Here we go. We have examples. Bad examples. Figured out add scatter. Okay. You have to do that too. Big dot add. Scatter. Figured out add scatter. Right. So we can have our x is equal to our xys array. Which one's the 0 or the 1? One is the x and one is the y. And the x is the 0. Y is equal to xys. 1. Is that everything? Of course, it wasn't everything. Because mode is equal to. Looks like the right color. Big and underscore. Yay. Mhm. That's how big it is. And also we want it to be dark mode because everything is better in dark mode. Don't need to have the width, height, and split. Also, pick this up. You need a square. I don't know. Maybe that works. Maybe it's wrong. Figure object has no attribute. Add layout. Need the layout? Seems like an option. We made a circle. And that is because we did an array, vector array, 2D, rotate around the theta, got the y and the x, at least circle-wise, trigonometry and such. The lines parallel space, 2 pi, which is like the entire circle, 120 points, and point false. Go from 0 to 2 pi. Get rid of this. Have an array of theta values for your vector, rotate, put them all together, make a subplot, bam. Also, I forgot to point out my second angle is back there since I'm using the bed to record. Because I'm a peasant. But okay, so this is the second part of part 1, where we have to create an oval around our circle. So we're stretching the matrix that we had. So define a 2 by 2 stretch matrix. And so what we're going to do is we're going to do the array. I can type. Let's go. It actually worked this time. Okay. Yeah. Um, 2, 0, and 0. I think. Ooh. Mm. Aww. The villager noises in the. Remember, the reason why there is this error is because you have to put another. Yay! See, now it worked. Apply our stretch matrix to our XY. So we're gonna have stretch underscore XYS is equal to, let's make that stretch underscore matrix. That's that. It worked. Okay. And now we do my favorite part again. Big is equal to make underscore subplots. And then we have to do all of our plotly syntax. So we have the big dot add underscore scatter like rats. Don't look at me, I'm gonna laugh. Okay, so x is equal to x, the array 0 I to xys 1. And this is just what we did. Mode is equal to what business people like to play with. Okay, figure. I don't. X is equal to I think it's going to be stretch or XY. Boom, boom, 0. Oh, T. I didn't. I think that was going to be stretch. Yes. 0. That's why, because I did the outside. Mode is equal to markers. Oh, need the usual. Yes, I do. I'm going to update underscore at x-axis. And we want to do that so that it's a 3 by 3. How did we do that last time? We didn't. Right, guys. Just gonna steal this from up here. Mouse tool that we'll use for later. And then we had to have it just range of 3, let's hope that worked. Who knows? And then I'm gonna do the same thing. Y-axis. Range. Okay. Not great for the ending. I really don't think I mean that, but I could be wrong. Let's see. Invalid syntax. Let's look up here. X is equal to X, Y. We're gonna add scatter. Ah, I love equal signs, you know. Let's see, these need equal signs. Whoa! What did I do? Oh my goodness. I found 2 mistakes, possibly. Oh, or actually, maybe I don't need that. I don't know. I did a little bit of mining offline and put my X here. Let's see if that fixes it. Nope. All right. Okay. So I deleted an equal sign. I'm gonna delete another equal sign. Let's see if that works. Why do you hate me? Why do you hate me, bro? Object of integer has no len. Okay. It's range equals apparently. Oh, thank you. Oh, yes. Okay. Yes. Recording in progress. The situation. I'm just kidding. I'm gonna clip that out. Okay. So now we want to rotate our stretch. Wait. Underscore matrix. Chill. Underscore matrix. And then we want to do this by pi over 6 at, and then let's make sure I'm doing this right. Stretch XY. There we go. All right. So then after we do that, we can basically just like just steal this because I'm not doing it again. I don't know about you. Just make sure I'm not missing anything. Control V, make subplots, and basically, see, V, but let's call this rotate. That was my second angle. No, it fell off the chart, dude. Everything. What's up? I'm keeping that in there. I don't care. This is suffering, and you will suffer with me. We're good to go. Wrote. Why doesn't it say that it exists? It exists up there. Wrote stretch matrix. Maybe no, maybe it should be XYS. XYS. Yeah. Okay. Wrote. My posture is terrible. I'm making Calvin crack up over here. He hates it. Let's see. We did it. We rotated it. Let's go. Yeah. Okay. Let me compose myself. Okay, we're recording again, and I just wanna see what happens when we rotate it by different angles, you know? Oh look. Let's do just pi. Oh, wait. We should probably just do this. Bam. There we go. That's what we mean. That's what we like to see. Okay. Okay, so now we want to make a subplot for our helix. Okay, yeah. And specs is equal to it is picked. Type. Oh, we need the surface. We need the surface. Oh, but we need a lot more. I need to cut this. I bet it's going to give me a silly, goofy error. Let's see. Yes, and is it rows? Or okay. So now what we're going to do is we're going to generate an array of S values, and then we're gonna do X, Y, and Z afterwards. Cool, and that's gonna be a length space function. Okay. And then space. Okay. And we're gonna go from 0 to NP. NP pi. And so 2 pi is one full rotation. That's 1,000 of these, but one full rotation on a circle, right? And so 6 pi would be 3 full rotations on your circle. And then your x is going to be cosine of s. Y is going to be sine s. And this is trig. And then this one's going to have to be, I think, NP. Pi 6, I believe. Because if you, well, if you think about it, it's probably 2 because 2 pi. We'll test it out later. But let's do, I'm gonna make fake stuff. Can we do a control and then, oop, no, don't do that. Well, we're gonna have to do this, control C. And we need something to be this, but we're gonna change it around. So control C. And control B. X is X. Huh? X is X. Is that what I said? I feel like I didn't. And let's go with markers for now and then make it bigger so we can go up. See what happens. Maybe I've just made a convoluted circle, even though it looks on oval. Let's see. Don't think this is it. X and Y. Wait. Z is equal to Z. Then we have. Can we have markers? Don't. Where did I go wrong? Figure dot add scatter. Okay, X is X, Y is Y, Z is Z. Okay, we have everything. But where did I go wrong? Can't see the top of my error. Oh, here it is. What does it say? Did you mean X? No. This is still not 3D. I've no longer gone wrong. Look at it. Isn't it beautiful? Okay, so let's see what happens if I change 12. You have more spirals. Okay, let's go back to 6, please. Let's see what happens if I change this though, because I'm actually curious. Ooh, she's short. Because the Z direction has changed. Or not direction, but the shorter. 1/6 or 1 over pi over 6 versus 1 over pi times 2. Should have said pi times 6. It's okay. But that is our helix. Now we have to do our Freinay-Serre part. And let's go check the homework. Minor radii of 1, 0.5, or major and minor. And then, So we're going to do our, okay, our radius. Slope in the Z direction is equal to, did we say? It's 0.5. A is equal to 1, and then we have 0.51. B is equal to 5. Okay. I don't know. We use the points. Now that we've set everything equal to, or set all of our variables equal to a certain number or defined them. Now we have to define our helix by points S, position R, or radius R, and then MC, and how it goes up. And then, uh-oh, wait, I did something. But I think, there we go. Okay. So we want it to return an array of our, don't look at me, MP cosine of S. And then R times MP dot sine of S. And then we have MC times S, I believe. And we will see. Then we have to define our friend A separately. We're going to call it though. Well, we go back to the homework, DRDS. ResNet. Luna. Luna. The cat is in the room now. Okay. I have a cat here, but Renee's already. All right. DS, right? Oh wait, no, I should probably DS equal to the jux dot copian of, okay, it's gonna be our R, this one. Now we have to have R. Renee Sherry. We have to do our tangent now. We have to define tangent. We'll have T. Wait, I always forget. Okay. Have this result dr d ds score res for every point s. Oh no. And then after we have that, we have to have we have to do a linear algebra normal, and we don't need to have an equal sign for the return of dr ds divided by, and then we have to have CNP dot lin algebra oops, what did I do? Let's see if that worked. It looks like it worked. Except for the fact that we have the RDS res updating. Oh, that's what we want. Now we have to find this Okay. And so since this is supposed to be a closure, we're gonna have to have this over. Tab, tab, untab. And so then we need the range of the tangent ds is equal to the Jax dot Jacobian of tangent. Okay, now we have to define our normal. This is set up the same exact way as above it. And the tangent ds res, right? DRDS, yes, res is equal to the tangent ds res, and then have an s. And then we want it to, wait a second, we need to have these. What's in there? Return of the Jedi. Wait, no, we don't return with the DRDS. Wait, the tangent res over np dot lin algebra normal of the tangent ds res. After this, oh no, where's your my second angle? Yes, return tangent and the normal. Okay, well, apparently. Okay. So, oh boy. And the last thing is equal to our resonance area of r lambda s helix. And so then what we need is r s, r is equal to r, and r mc is equal to mc. Luna, hush up. Expected. Yes, there was an expected. No wonder it did. Okay. And so that should be the final of using closure, explain, and code a higher order function that returns the functions that calculate the Frenes array, tangent, DRDS, so and then the normal, which is the derivative of the tangent, or DTDS, vectors for the helical curve. And so that's what this is. Ooh, not that. Yeah, so define the helix, all that, define the Frenes array, and then you have the tangent and the normal in that, and then all this at the bottom. And up here we have our helix, this eyeball, and circle. Thank you. And my meeting time is ending.